Hello again. Happy weekend. Uh, I want to continue talking about arrays, but this time I'm going to look at two-dimensional arrays. Actually, I believe C++ can have one, two, and three-dimensional arrays, but I don't want to fool around with three at this point. What we're looking at is data that we want to represent as a table. There's a lot of this kind of data around. Mathematics uses matrices. In fact, matrices are used for things like animation and in Hollywood films because they represent what's called linear transformations. So they're pretty important. We have a whole course on linear algebra involving matrices and what they are. Now, another possibility would be a tic-tac-toe board. I've shown you one here where I use X's and O's, and I use a B for a blank so that it looks more like a tic-tac-toe board. So what I'm going to try, well, here's another possibility of representing grades, where we have each row is one student, and each column is one grade. I'm going to try to write a program to read a set of grades and compute the grades for all the students. And I guess I could print I haven't done it, but I could do the average grade for each test. Now, I don't want to type a lot of data in, so I created a file for this. I have 8 names of people, and I have 10 grades for each person. I made this totally randomly, so don't try to find any pattern in there. It's not there. I put that out there on test grades so I could test the program. So how am I going to do this? Well, first of all, you need to know how we declare a two-dimensional array. So we will use the case with 8 students and 10 tests. We declare the array as, now they're all going to be integer grades, so we declare it as int, and I think I use grades, and then A and 8 and 10. I look at that as the row and column. RC. That's the way I remember it. It's the way the computer puts it in when it writes them out, puts them in order inside it. It writes the first row, then the second row, then the third. I believe that's the way it does it. I'd have to remember, to be honest with you. But basically, that's the easiest way to remember it. Treat it as rows and columns, and you'll have a better chance at looking at it. So that means, for example, that if we look at this set, this number right here, let's pick a different one, right here, this 10, that I can't seem to get to stay alone, it is in the 0, 1, 2 row. Remember, we start counting at 0, and the 0, 1, 2 column. Now, this one over here, the 8, is in the 1 row, and the 0, 1, 2, 3, 4, 5, 6, 7th column, 7 column. So every place in this table has a row and column. And every one of those rows and columns is an integer variable because we declared it as an int. Now, this is the way that this particular language goes at it. I was used to a language that didn't have the two sets of brackets, that used a comma instead, but this is the modern language, the way it does it, so we'll take it this way. And actually, it's not as hard as some for declaring things. So that's what I want to do. I want to write that program. So I took the liberty of writing it already, so it wouldn't take us a long time. But I'll talk about it as we do it. Now, again, I wanted to read it in, remember, so I needed F-stream, and I needed using namespace standard. And I declared a string of names, a string of grades, the total for each person, and I probably should have a total for the test. I didn't put that in yet. Why don't I do that? Double test total 8, and I'll start that at 0 also. So now I've got IF stream, test grades. I opened it, I gave it the same name. For each student, I am going to read the student's name. Now, if you look at the file, there are no blanks in the student's name. So I don't need getLine. I can read it as a string. I don't need the getLine. I should be careful here. I'm not using the special class string that we used in the projects you're working on. I'm using just a plain old string, and it doesn't have all the good things that we can do. For example, the getLine would not have worked because it only works for the other kind of string. In other words, I would have had to put a # include string if I wanted to use getLine. Now, it's very simple. I read in the names, and to see that I'm working, I print them out. I want to make sure I got it right. Then I'm going to read in the grades. Now, this is a pretty standard approach to an awful lot of the way things are done with two-dimensional arrays. You end up with 2 loops, one taking you through the row and one taking you through the column. So I go row 0, column 0, row 0, column 1, row 0, column 2, row 0, column 3, etc. I set the row as 0, and I run through all the columns. Then I increase the row to 1, and I run through all the columns. It's a very standard approach. Now, I'm also going to add that I'm going to add to the test total of J, which J is the test, what we have already, plus this grade that I read in. Grades I and J. Notice again that I can put anything in there, anything that makes sense. I don't have to put I and J, but it worked better to put I and J because that's what works for these loops. So that's computing the totals for me. Now I start printing out. I printed out the name of each person. Then for each of the of the columns, each test, I printed out that person's grade on that test. I represents the person, J represents the column, the test. Then I printed out the total for that test. For all the people in that particular test, I printed out the total. And I had to divide by 10 because I wanted an average. Now, when I finish all of those, I'm now going to print out the test totals. So I'm going to say for int I equal 0, I less than 10. Now it's 10 this time. I hope I did that right up here. I didn't. The test total should be 10 because there are 10 tests. So for that, I plus plus. Now I'm going to print. All right, first I'm going to print out some words. So I'll print out in set W12, I'll print out test little averages. And that's not above 12, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, it is. It won't be now. So we'll leave it there. Now I'm going to put these out in the same way I put these out. I'm going to have set W. I think I'll go with 6. That should cover what I have. And I'm going to put the test total. Oops, test total, bracket I, divided by there were 8 students who took the test, so I have to divide by 8. And then when I finish printing that line out, then I'll print the end out. Now, these are 6, and unfortunately the grades in each test I put down as 3, so I'm going to change that to 6 to make it look better. I think that'll fit. I have 72 plus 8. It should just fit on the line. We'll see. So let's go to it. I printed the test average every time. Well, that was a mistake. So I will print the test average here. See out set W12 test app. And then here, I only print this out. And now we'll run the program and see if it works this time. Looks much better, although it's wrong. 1, 2, 3, 4, 5. It could be wrong because I didn't give it enough room, but I don't think so. I think it's wrong for another reason. So let's take a look and see if I did it right. I'm averaging all the test totals. Now up here, when I computed the test total, it was with J. So the test total of J is the test total of J. How about plus sign? I knew something was wrong. Let's go to it. That looks much better. The numbers look like they're probably right. Now you notice I didn't panic when I made a mistake. I went in, I figured out what was wrong. Usually it's a typo. But it could have been worse. I could have had to rethink something. So I'm going to take this program and copy it for you into what I will be. I hope I copied it. And I don't think I did. All right, now let's copy it. Control C. Take it over here. Let's see, where am I? Here. And here's the program. And here's the output. Now, output. And now I'll copy the output. And take it back. Now it doesn't come out very nicely on this page, unfortunately. The only way I can get it to come out better is I've got to cut the size. So I'll cut the size to 14 and it'll fit better. Also, to make it look better, I will switch to an output of Courier New. Courier New has an advantage. All the letters are the same size. Unfortunately, they're big, so I may have to get them to fit, I have to make them very small. Or I have to change the layout to be landscape. Now I think they'll fit. Yeah. So that's one way to do it. Now, a second program I'd like to write is a program to read a tic-tac-toe board and determine if anybody has won. I have the program. It's right here. The only problem is that when I tried to run this program, I got a virus. I've had this happen with some of the programs you sent me. I don't know why. I'm just going to leave it here. I'm not going to run it, and I suggest you don't copy it and run it, because if you do, you'll probably get a virus. I don't know why, but it happened. Now, the last thing I want to do with this right at the moment is show you one of the more interesting kinds of programs that we can do. This is a famous program. It exists on the web and anywhere you can look. It's due to a man named John Conway. He was originally from the United Kingdom. I can't remember if it was Oxford or Cambridge. And he wrote what they call the game of life, in the 1950s. John Conway is brilliant. He's the only man to have invented a new type of numbers in the 20th century. He's also eccentric and a very dynamic and unusual lecturer. I've seen him lecture. He has gotten up on top of the table as he's been lecturing. He lectures in an old t-shirt. He might take off his shoes. He's a character. Unfortunately, he had a stroke a few years back. He has come back from it. I've seen him lecture since he had the stroke, but he sits down now. He came to the United States and he went to the Institute for Advanced Studies at Princeton. This is not Princeton University. This is a university where there are no classes. It's just professors who are working on very advanced topics. This is the place where Albert Einstein ended up in the United States. It's also the place where John von Neumann was working. John von Neumann was one of the earliest pioneers of computer science. And the method we use for programming, where we put a program into the computer and execute the steps from memory, is known as von Neumann style programming, because he was the one who sort of championed it in the beginning. I've not seen him. He was before I could be going to any kind of talks and understanding anything. But was supposedly absolutely brilliant. Now, the question that people are asking is, can you begin with a finite set of organisms in a grid, define rules for birth, death, and survival of these organisms, and have the organisms grow without limit? And this had a fancy name in mathematics, the cellular automata. At that time, and for like 3-4 decades, I think, something like that, Martin Gardner wrote a regular column in Scientific American called Mathematical Games. Basically, the column was worth the cost of the magazine. The columns have been collected in lots of books, and you can find out much about Martin Gardner if you look on the internet. What he did was he put the game in, and he gave people some challenges. And it just took off. The boys from MIT had a ball with it. They were coming up with all kinds of ways to play with it. And there have been many, many interesting patterns, and I'm going to try to show you some of them. Now, here's the idea of the game. We start out with a two-dimensional array of cells. Technically, it's supposed to be infinite, but I don't have too much ability to make it infinite. I don't feel like doing it, so I usually curtail it a little. We call each organism a star, and each of these cells has 8 neighboring cells. Now, that's, of course, not counting the borders, but what I do is I don't let anything go into the border, so I don't have to worry about the exception. So if I have cell 3,4 here, then it borders cell 2,3, 2,4, and 2,5, cell 3,4, and 3,5, cell 4,3, 4,4, and 4,5. Now, it's important that you understand what we mean by neighboring cells. They're the cells that touch, either diagonally or along a side, any cell. Now, here are the rules. If a cell with a star in it has 0 or 1 neighboring stars, in other words, those 8 cells have either 0 stars in them or 1 star in them, it dies of loneliness. If a cell with a star has 4, 5, 6, 7, or 8 neighbors, it dies of overcrowding. If a cell with a star has exactly 2 or 3 neighboring stars, it survives. Well, that handles death and survival. What about birth? If you have an empty cell and it has exactly 3 neighboring cells, a star is born in that cell. So it takes 3 neighboring stars to produce a star. And the most difficult thing when you're programming this is that all changes happen at once. It's not incremental, which means that you have to keep 2 grids. One grid has the old information, and then you're putting the births, the survivals, taking care of the deaths in a new generation, and then you can make that the old generation for the next time around. Everything happens at once. Now, there's a lot of little things about it. Here's one. This is one of the simplest of all, 3 stars. Now let's see what's going to happen. Well, this star's lonely. It's going to die. This star has 2 neighbors. It's going to live. This star is going to die. It's lonely. But right up in this cell, there are 3 neighboring stars. So a new star is born. And in this cell, there are 3 neighboring stars. So a star is born. Now, that generation looks like this. And guess what? If we look at the next generation, that star dies, this one survives, and a new one is here, and a new one is there, which looks suspiciously like the first one. So this is a oscillating pattern. It's called the stoplight, blinks on and off. Now, I'm going to see if I didn't do this before I started this, but I'm going to see if I can get myself one of the better places on the net for this. So I'm going to have Game of Life, Martin Gardner. October 1970. And here's some of the pictures that you can see. This one is the one that I was talking about. This is the blinking lights. This one is one where things sort of move around. A lot of strange things that happen. This one is known as the glider. It starts at one place and glides across the screen. See, there should be 1 or 2 more. This one produces more. You'll notice as it goes down towards the right, it produces more and more gliders. It's a bullet, a generator. Now, for our purposes in this screen, the bullets, the blocks disappear, the gliders, but they go on infinitely. So there'd be more and more of them. And this one, if you'll notice, moves across, and then all of a sudden something weird happens. That's because we hadn't seen the whole thing before. Now, it does its thing, it starts building, things come back in, and things go wild. The most famous one, which isn't in this one, so I'll have to go and get it, is I'm going to put Game of Life, the Cheshire Cat. Here we are. Now that looks like a cat, doesn't it? There's the cat's grin. You may remember from Alice in Wonderland, the cat disappeared except it left its grin. That's what this is all about. People do have fun with games like this, so there's no doubt about it. Now, I wrote this program, and I'm not going to try to go through it step by step. It would take forever. What I'm going to do is I'm going to look at the program and talk about some of the things in it. So the first thing I want to note is that I wanted to make my life easier. I did not have to worry about the edges. So what I did was I had an n by n grid, but I put the n by n grid inside another grid that had an extra right column, an extra left column, an extra top column, and an extra bottom column. That way, I did not have to worry about the borders. I call it a DDT border. Nothing can grow on the edges. I won't let it go out to those rows and columns around the edges. So the first part of the program I needed was I had to read in an initial generation. I put that in the initial generation in OldGen. I printed out OldGen, and I asked the user if they wanted a new generation. And if they did, I created the new generation in a different array called NewGen. I printed NewGen, and then if they wanted another generation, I had to move NewGen into the OldGen so I could repeat the way I generated. So I needed two two-dimensional arrays. And I needed to figure out how to get the neighbors. So I found that to be pretty easy. Now let's take a look at the code. It's in here too. Now let's go over here and look. This program I use oh, pardon me, that's not the one. I got to close that one. And I want to bring up Conway Life. All right. We use the constant concept. Now you got to look at this. I'll skip those for a minute. I'll go down here. There's the declaration of OldGen and NewGen. As I told you, I wanted one more than n on each side. So I wanted n plus 2. And that's what I did for the rows and the columns. I initialized generation 0 so that every single place was a 0. 0 means no life, no stars, period. And then I generated the first generation. Now, this is the strange part. First of all, I had to pass in the IF stream. It wouldn't let me do it by putting the IF stream above the int main. It had to be passed in. And there were a few little restrictions on passing it in. So let's go up now and look at the header for this particular program. Here is the first one on line 9. First of all, look at IF stream. It's got an ampersand. That's because IF stream has to be allowed to change. The function, as it's reading from it, will change it. And those changes have to be known when we return from the function, because we're going to use the function again. And IF stream has to have been modified. And basically, it has to have been moved so it'll read the next line, not the one it read before. So you need that ampersand. I can guarantee that because a few minutes ago when I tried to do it without it, it went no. Now, the funniest one is how you pass a two-dimensional array. This seems very, very strange. First of all, you don't put in both of the sizes. If you do, the machine presumes you're passing one thing in. So you don't do it that way. You pass in just as we do with one-dimensional arrays. We just pass in an empty bracket, an empty set of braces to say this is an array. OldGen is an array. But OldGen's a two-dimensional array. So you'd think we could just get away with an empty braces and another set of empty braces. But there's a subtle problem hiding behind everything. The computer needs to know how many columns there are. Because when it computes an address inside OGen, it takes the row number and multiplies by the number of columns, and that gets it the beginning of the next row of the row. So it needs to know the number of columns, and it needs to know it when it's translating the program, when it's compiling the program. That's a subtle point. I'm not expecting that you will really grasp it right now. What I'm saying is it has to do with the way we store a two-dimensional array. Remember I said the whole first row is stored. So that first row has n plus 2 elements in it. The computer needs to know that when it goes down to get, say, OGen 1, 3, it takes the 1 times n plus 2 and adds 3 to it, and that gets it to the right place. That is the place in the whole list of this particular array, two-dimensional array, that it finds. Now you'll see I've done that all the way down here. It's just something I had to do. And I had to do the same thing with outbar for the OF stream. Now there's one other one I want to point out to you. Oh, the copy was very simple. OGen, I'll show you this when we run it in a minute. All I do in OGen is ask, where do you want to put the stars? And I just keep putting them in many as I want. OutGen just prints it, as I said before, this double loop, double for loop, is the workhorse for two-dimensional arrays. And then copy, and now generate. I needed to know the number of neighbors. So how am I going to get the number of neighbors? I wrote a function for it. The number of neighbors, now remember, I send in the row and column. So let me see, I gotta go just a little further over so I can get it all in. That didn't work. I think that'll work. I put them out pictorially. The OGen row column is in the middle of the second row there. The column above it, the row above it, is all the things above it in the grid. Remember I said it was row minus 1. If we're in row 3, then the neighbors above are in row 2, and the neighbors below are in row 3. So I put in the plus 1s and the minus 1s. And the columns are the same way. The column minus 1, column plus 1, column. And that's the way you do it. You just think it out and do it. It's not trivial, it's not hard, but you have to make sure you are following it and do it. So that's the program. Now let's see how this one works. Now, the input's going to be coming from a file. I just didn't feel like typing all the time. So I've got myself a file. I'll open the new file for you. Call it bar. I'm giving it 1, 2, 3, 4, 5 items. I can give it more if you want to, but that's the one I use to test it. So let's see what happens. All right, there's the first generation. I put 5 items in with 1 off on the side. Yes, I want the next generation. Now look what's going to happen. The star in the extreme left here will die. The two middle stars will live. In fact, the three stars will live because that star has two neighbors. Those three stars will live. There'll be two new stars up above and two new stars below, three new stars below. So let's see if that's right. Yep. Two, the three that survived, and down below. Now, if you look at this, the middle star is dead. In fact, the star in the corner has three neighbors. It'll live. The star in this corner has three neighbors. It'll live. But this star has four neighbors. This star has four. This one has 1, 2, 3, 4, 5, 6, I think 7. It is going to die. This one has 4. So you're not going to get too much survival. From what I can see, only these two corners are going to survive. But there's going to be some births. There's going to be a birth here. There's going to be a birth below and on the side here. So we will get some new ones. And that's what happened. So we got ourselves a little bit different pattern. Now the question is this settling down or is it going to never become steady? So let's try another one. Well, we still don't know. Let's try another one. It's looking pretty nice. And I don't know if I saw that one before. And I know I saw it now. And if you look at that, every star has two or three neighbors. And every empty space does not have exactly three neighboring stars. Some only have two, some only have one. And the ones in the middle there, they have too many. So I'll end it right there. Now it happens I actually have the file that has the output. I put the output on a file also in case I wanted to see it. And I think I just wrote this over it. I hope not. No, I think I'm okay. That's bar. And that is what I wanted. So it's open out bar. And here's what you get. You can see the different generations. And it was kind of fun to play with it. So that's the game of life, and that's the idea of two-dimensional arrays. I'm going to get you a problem with two-dimensional arrays, maybe tonight, but definitely I hope by tomorrow. So you'll have something to try for two-dimensional arrays. After two-dimensional arrays, we're going to talk about vectors. And actually, vectors are more or less the first place that we are getting out of just catching up with all the techniques you know from Python. As I said, some of you know about classes. That's coming after the vectors. And at that point, we'll be beginning to go into detail on newer things that you may not have yet done in Python. So I'll see you later. Have a good rest of the weekend.